In this most obviously technologically and scientifically advanced point in mankind's history, there seems to be a lot of confusion about science in general today, and I don't mean in terms of the sheer complexity of particular scientific principles. I mean in the way that different types of science, broadly speaking, fit into the general framework of what science is and why we need it and why we do it, and how different subjects relate to practical things, technologies that we use in our life, and how they relate to each other. For example, a lot of people have the impression that very advanced math, very complicated symbols on a page, stuff like this, people wonder how this could have any practical application to the real world. And yet at the same time, people are certainly aware that somehow all this advanced science and math absolutely plays a role in this amazing technological world that we live in that didn't exist at all 100 years ago, and for a lot of things like our smartphones, not even 20 years ago. And then you have things like medical science, where people again are so clearly aware that modern medicine has extended our lives and allowed us to live healthier lives, less painful lives. And yet at the same time, we're inundated with scientific studies in the media that the next day are disproven. Coffee is good for you, coffee isn't good for you, this causes cancer, this doesn't cause cancer. And of course, this creates a confusion. We seem to know so much. How could we be so wrong about these things? Then you have things like social science, where the implications of the scientific result seem to have political implications. And just based on the politics of it, people may have a problem with the science. And then you hear about things like data science, which companies are using to process enormously large amounts of data that are collected in this information age and use it to discover trends and learn new things that we didn't know before. Data science, that's a big buzzword now. So people wonder, what is all of this? How do those things fit together? What is the difference between math, science, and technology? Medical science versus medical non-science, social science, data science. Where does it all fit together? What does it all mean? And the best place to start is simply because it was the first historically and remains today the foundation of science, is with what's called generally physical science. Those are the things that you study generally under the topic of science in school. That is physics, chemistry, biology. In the 16th and 17th centuries, building on the hard work of a great many people, notably Galileo, Newton, also Alhazen and Baghdad, we had the scientific revolution, which begins science as we know it. And the things that they discovered then generally today fall under the field of what's known as physics. They came up with a way of doing science which gives us the recipe for how it's still done today in physical science, or in physics to be more precise. This type of science can be called in general predictive or inductive. It's a type of science where we make specific predictions and then we test them. And the real recipe or guideline of how that works is we do experiments, we learn things from those experiments, we take precise data, we use the experimental data in combination with mathematics to formulate physical laws, which are generally just mathematical equations, but which have the absolute status of truth in any experiment we can expect to conduct. We make new quantitative predictions, specifically causal quantitative predictions. If I do this A, it results in this B. When I push this ball with this spring compressed exactly to this length, it moves exactly on this path at exactly each of these points in time and ends up there exactly where we predicted it to be, to this number of decimal places. We test our predictions experimentally, and if they're correct, we repeat. We take these and go back to the beginning of this recipe and try to combine newly discovered laws with other experimental data and formulate even further new ones. Of course, it's not so cut and dry as this, and we really don't want it to be. Because if everything works out, if our predictions match experiment exactly, all those decimal places, it's quite amazing and it's quite an achievement, but then science ends. If we understand everything, science is over. We need something to break down. We need a prediction to break down. We need an experiment that we didn't have a theory of in order to discover new science. So yes, this perfect recipe has a couple of very important caveats. But with that, again, the foundation of this predictive science or physical science is physics dating from the 16th and 17th centuries particularly. And an example a bit more magnificent than pushing a ball and seeing where it goes is the motions of the heavenly bodies. people always knew that Halley's Comet came about every 80 or so years. But because of its highly elliptical orbit, that means the orbit of Halley's Comet around the Sun differs greatly from a circle. It's an elongated ellipse. And the speed with which the comet moves is greatly dependent on where it is in that orbit. Because of that, combined with the motion of other planets and Earth, complicates how we would predict when Halley's Comet would return and how we'd observe it from Earth. Newton formulated his universal law of gravity and his famous work, Principia Mathematica Philosophiae Naturalis, the mathematical principles of natural philosophy. In it, he explained how the orbits of heavenly bodies are due to the gravitational force of the sun. And then Halley, this is how he got his name on the comet, Halley then took Newton's laws and plugged in the numbers, which is how we'd say it today, but when computers didn't exist and even paper and ink were quite limited and hard to come by, it was a lot more difficult. But he did it, and he figured out exactly when Halley's Comet would come back based exactly on Newton's universal law of gravitation, and it proved correct. An amazing, great initial success of Newton's laws and the scientific method in general. Other parts of what goes under the heading of physical science or predictive science or chemistry and biology. And the story of chemistry was that it's something that becomes a real science according to this recipe of making theoretical mathematical predictions, testing them experimentally. It becomes a real science in the 1920s after the development of quantum mechanics, after cracking the mysteries of the atom. Chemistry, of course, goes back to ancient times, alchemy, and by the 1800s, by the industrial age, people had recipes to make chemicals. They understood if you took this chemical and you mixed it with this chemical and you heated it to this temperature, then you could make this thing, this other substance. But the way they got there was by a lot of hard work and trial and error, and a lot of people dying and being injured in lab explosions and inhaling and ingesting toxic chemicals. And they didn't really have a predictive theory for how you made a particular substance or what its properties would be and why. So starting in the 1920s, and by the way, this is the connection between science and history, this was all happening in Europe, especially Germany in the 1920s. This was the time of the Weimar Republic, the time between the world wars, a transformative time in human history. This is when and where quantum mechanics was developed. With the formulation of precise laws of how atoms interact, and of course, that's skipping over the whole aspect of history of how do we know atoms exist, what's the proof of that. But starting with these laws, chemistry greatly advanced in the 20th century. And we're at a point now in chemistry where chemists can come up with a material that they want to make. They can figure out what the structure of atoms and molecules will be based on the material properties that they want to create, and they can make it. That's, of course, the ideal case, and it doesn't always work out that nice and simple, but that's pretty much where we're at in chemistry. Biology is, of course, inherently less quantitative. Before Darwin, it was all about taxonomy and grouping different plants and animals and seeing what their structure and anatomy was. Darwin gives his theory of evolution, which greatly advanced biology. And it's not a precisely mathematical theory, but in fact, Darwin's theory of evolution is probably the most important and powerful law of nature that is conceptual and qualitative in nature as opposed to quantitative and rigidly mathematical. But it's only in the past few decades with the rise of molecular biology, that is the understanding of biological organisms at the purely molecular level, that is to say, understanding biology essentially as just a very complicated application of chemistry, that increasingly so biology is a predictive science. We can understand that this drug in combination with the molecular understanding of your cells will do this. This gene will code for this protein, which will do this, etc., etc. And of course, that has to do with the atomic level understanding, which goes back ultimately to the understanding of quantum mechanics, first cracked open in the 1920s. And on the subject of atomic science and quantum mechanics, you may hear about the unusualness of it or the craziness of quantum mechanics, Schrodinger's cat and this and that. Well, all that aside, You better believe that quantum mechanics is real and practical and built into all the technology that you use in your everyday lives, from microchips to lasers to pharmaceutical drugs.